Hey, Jonathan, how Vector 4 is doing?
Vector 4?
Yeah, because Vector 3 is completed, I think, now.
JVector 4. Um, well, shoot, man. If you want a sneak preview, we may have some news to talk about with GPU acceleration for JVector 4, but that's super
Oh,
super early, and I can't promise any specifics yet.
this was a joke, actually, right? So I know that JVector 3 is completed. And so what the major features or what happened between JVector 2 and 3?
Okay. JVector 2 was a fairly straightforward adaptation of Microsoft Research's DiskANN search indexing to Java and to Cassandra. And so that means that you have a two-pass search where you have a coarse index that works on a graph whose comparisons are done with quantized vectors that are kept in memory. And then you refine the results of that search by using full resolution vectors from disk. And so JVector 3 has been, how do we go beyond this DiskANN design and improve it on two dimensions? The two dimensions that we were feeling pain with from our hosted database as a service were around compression levels and around how large my index can get, and these are related problems. So the reason why we care so much about how large the index can get is that your search time is it's linear across the number of index segments you have, like the number of physical indexes you have, but it's logarithmic within an index. And so if you read the HNSW paper, if you read the DiskANN paper, if you read a lot of these papers, they're about how do we give you logarithmic search performance as the index size increases. But once you reach the limit of the largest the largest graph that I can construct, then I have to spill across into multiple separate segments, and then combining the results from those segments is now a linear process. And so the state of the art with DiskANN, and I think this is true for most of the other vector indexes as well, is that you build the index using full resolution vectors that are kept in memory. So that's the main bottleneck that you have, is the size of your data set in memory. So JVector 3, we added the ability to build the index using compressed vectors without losing accuracy. So that's the first big one around increasing the size of those indexes that we can build. And then the other pieces in JVector 3 are around different types of how do we improve the compression that we're doing.
So with JVector 3, I will need less RAM to achieve the same?
Yes, you will need less RAM both to build the indexes and to serve the indexes. Building the indexes because of what I just discussed, and serving the indexes is actually coming from a different optimization that we made.
Mm-hmm. And how big or how much RAM is, how to call it, recommended? Of course, it depends on the size of the database, but I mean, what is the typical size? So if I will, yeah.
Yeah, so the largest, not the largest, but a good reference point is the blog post that I wrote for Fujay a little while ago about indexing all of Wikipedia on my laptop. And so that indexed the 41 million rows of a Wikipedia dataset that had been chunked, in other words, broken up into smaller pieces. So it's not 41 million articles, it's 41 million paragraph fragments that are embedded separately and indexed separately.
This was the size of the embedding, so I decided to chunk the articles into pieces which are for which the vector was calculated, right? Or how to call it,
yes.
Calculated, right?
Yes, because the larger the piece of text that you give to an embedding model like Cohere or like OpenAI v3 Small, or on the open source side like the E5 family, the larger the piece of text you give it, the less accurate it's going to be about any of the specific contexts that are contained in that text.
But it depends a bit on the dimensions, right? The more dimensions a vector has, the more text we can pass, maybe. Is it true?
There is something to that, but there's also diminishing returns, right? So Cohere's embedding vectors are 1024 dimensions. OpenAI v3 Small is 1536. OpenAI v3 Large is double that. And then that's about the biggest that anyone has. And OpenAI v3 Large is not twice as good as OpenAI v3 Small. It's less than twice. And so you do have this diminishing returns as you get it. So nobody knows how to make a vector embedding model that can capture all of the information in an entire Wikipedia article accurately. And so we break it up into smaller chunks.
How long did it take to index the entire Wikipedia on your laptop?
About 6 hours. About 6 hours.
And which laptop is it? Is it Intel or M1?
This is an Intel 12900 i9. So it has 16 performant cores with 2 threads apiece, and then 8 efficiency cores with 1 thread. So it's a total of 24 threads.
And it was fully utilized, so 90%, 100%, or?
Yeah, effectively 100%. So one of our goals with JVector that we covered last time was it uses a non-blocking concurrency control design that lets it scale linearly with the number of threads you can throw at it, even when you're building or modifying the index.
And okay, and which model you use to create the embeddings, Cohere, or how you?
Right. So I specifically used the Cohere embeddings because they have helpfully already done this. They chunked up the Wikipedia articles, and they ran it through their embeddings model, and they posted it on Hugging Face for anyone to use. If you did it yourself from scratch, then it would cost about $5,000 in API calls. And so, I didn't want to do that if I can avoid it. And so I used the one that they pre-built.
Could you use, is there a model available which would do it locally for you? Like, Llama 3, you can run locally. Is there any local model where you can use for embeddings?
Not for Cohere specifically. Cohere is closed source. They have a service that they sell. But yeah, there are open source embedding models. I mentioned E5 earlier. And there's a few others that are fairly competitive that you could also use. But if you're going to do that, then you really need GPU acceleration to do that when you're talking about 41 million pieces of text. Otherwise, you're going to be waiting a very long time.
Okay, so you got the embeddings, and then so in your particular case, you just read the embeddings and stored that in JVector, and this was so it was not the calculation of the embeddings rather than just storing the embeddings in the vector, right?
Right, and the demo does the JVector piece, but then it also does the index for, given a JVector embedding ID, what was the article that it was originally associated with? So you want to be able to go both directions to be able to perform useful searches. And I used Chronicle Map for that second part, which is a I want to say it's LGPL licensed. I don't remember the license. It's an open source license from a fintech company. And it is by far the best performing option for, you want a map, but you want it to be larger than memory. So they implement the collections map interface but it can spill to disk. And there's a few rough edges that kind of come with the territory. It's a difficult problem that they're solving. So, for instance, they use mmap. They use a bunch of internal things in the JDK that aren't technically meant to be general purpose, and so you need to pass a bunch of add opens flags and so forth. But definitely the best option for that,
unsafe as well
that I found. Sorry,
unsafe. SunMISC unsafe.
I don't remember off the top of my head, but I'm almost certain.
Everyone uses that still. But are they using off-heap storage, or rather than they're flushing it to disk?
This was really cool, actually. So I measured it. I took a heap dump after I put around 1 million rows in, and I took a heap dump. And the Chronicle Map heap footprint was 2 kilobytes.
Wow.
So I thought it was going to have like some per entry overhead on heap, like a reference or something. But no, it's all off heap. When they say it's off heap, it really is off heap.
This is the Open HFT, right? Chronicle Map. This is the organization. Yeah, it looks like. Interesting. Never heard about that. So what it means is with JVector and Wikipedia, we could have now semantic search in Wikipedia.
Yeah, that's right. Yeah.
So what is missing? I could send you a prompt. For the prompt, I will have then to use Cohere, right, to create the same embeddings. Or this is what I wanted to ask you: are the embeddings compatible? So are Cohere embeddings compatible with i5, for instance?
No. So you need to, when you do your searches, you need to embed your search query with the same model that you embedded your data set. Is
there no standard on the horizon?
I don't think there's a standard on the horizon. And the reason is that all of these companies, OpenAI and Cohere and who else is in the embedding space? DeepSeek is open source. Somebody's doing it for code specifically, and they have a proprietary model, and I don't remember their name.
CodeLlama?
Anything that says llama is usually open source, so probably not. At any case, they have what they believe are their secret sauce, and they don't want to give that away. Okay. So everyone's competing to beat each other right now. So yeah, I don't think there's going to be a standard.
Okay. Okay, after 6 hours, we have, this is amazing still, right? After 6 hours, we have the entire Wikipedia in JVector. How big was JVector?
It's about 40 gigabytes.
RAM and disk?
That's the disk component. Well, so it exists in RAM while you're building it, and then we write it to disk, and then it's 40 gigabytes. And then when you go to serve the requests, you don't need to read the full 40 gigabytes in. You only need to read about 2 gigabytes in. And the distinction is that the 40 gigabytes includes the edge lists, and it also includes a bunch of GC overhead. And so the edge lists of the graph are 32 edges times 4 bytes apiece, which is 128 bytes. And that becomes the bottleneck when you're compressing the vectors down enough. And so the compressed vectors are only about 2 gigabytes, and then everything else is the edge lists. And the reason that you want to keep those in memory is that you're modifying them every time you insert a new vector. And so if you tried to keep that on disk, then I think the performance would be unacceptably slow.
So and how much RAM you dedicated to JVector?
So I dedicated 40 gigabytes to the JVM. So that was
40 gigabyte RAM.
For
and
everything.
This is a good practice to have the same amount of RAM as on disk?
No. So in practice, when we deploy this in the Astra service, we have index building machines separate from the request serving machines. And the index building machines are free to allocate much more memory because all they're doing is building the index. And then the serving machines, they're smaller, less expensive machines, and their job is to just serve requests. And so that's why we're okay with the footprint for constructing the index being larger than for serving it.
I already wanted to ask you this last time with JVector. What about single point of failure? So can be vector easily clustered or federated, or is there something like this? So if one, So
in the Cassandra space, when you give Cassandra a table definition, implicit in that is how to partition that table across the cluster. And so we use the first n components of your primary key as the partition key, and that controls how it gets spread across the cluster. And then each node in the cluster is responsible for indexing the data that is sent to it locally.
So using the same mechanism in JVector.
JVector is just the local index piece. So it plugs into Cassandra as I can index data for you. Yeah.
So what it would mean, is if you have JVector with the index, then it would be the same on every Cassandra machine, because it doesn't matter, right? You will have to replicate the file. Because where am I going with it? If I would like to search something, right? So what usually happens is I need association between Cassandra partition key and the JVector ID or the vector, because this is the association, right? If I would implement, for instance, reg, then in Cassandra would be my data, the text, let's say, or whatever, JSON. And I would like to associate this with meaning, which is the vector, in JVector, right?
Yes.
This is how it would
work. So JVector is like the low-level component, right? So if you're using Cassandra, you say create table documents with primary key ID. I'll declare that to be a UUID. And then my body, which is declared of type text, and my embedding, which is declared as type float vector 1024 dimensions. And so then I can just insert my text and my vector into that Cassandra table, and it takes care of managing the association between the two and indexing the vectors with JVector. So that's not something that as an application developer you have to deal with manually.
So what you did, you used JVector directly, which is unusual. Usually we would use Cassandra. So on every insert, you would write to the column, which will be indexed behind the scenes, right?
Right. And there's a reason for that, which is that the version of JVector in Cassandra, the current Cassandra release, is JVector 1.x. And so it's Cassandra 5.0 RC1 was just released a couple days ago. So Cassandra's not looking to change major dependency right now. And so to demonstrate JVector 3, my choices were either use Astra in local mode, which is actually open source. Not many people know that, but the branch of Cassandra that we deploy in Astra is open source. So I could do that, but then I'd have to do a whole bunch of explanation about, here's Astra and here's how I'm running it in local mode. Or I can just use raw JVector with Chronicle Map, and I thought that was an easier thing to explain to people.
Mm-hmm. I had a conversation with a client the other day, and they had this highly complicated object graph. So it was the edges between nodes were more important than the object itself. So, and my client asked me about queries, and and there are many possibilities, like Neo4j or something like this. But I thought maybe it is possible to use JVector to index the edges, and then use an LLM to have queries, full text queries, and to find the things. And I think this could work, right?
If you can represent those edges as vectors while retaining their spatial meaning inside the original graph, then yeah, that would work. But that's a fairly big if. I don't know how to do that.
Okay, because this was a quick. But because they already mentioned Cassandra, I was okay. Cassandra is interesting because we could use JVector, and then we have instead of full text search, full semantic search, right? This was the idea. Instead of using text comparison, we could use a meaning comparison, and actually it could or should work. There's actually no reason why not to. But I was just curious whether you had also similar ideas with Cassandra and JVector.
Yeah, just to make sure we're on the same page, JVector is not a generic graph engine at all. It just uses a graph structure to index the vectors.
Mm-hmm. Yes. So we would use, of course, Cassandra or Astra. This would be a cloud service, and just store the objects, and the objects are connected to each other. And for the connections, I would probably use single table design or something like this. And the objects would be then indexed, or the hash, or embedded.
Right. And yeah, you could absolutely represent an edge list in Cassandra, and then separately you could index a vector embedding associated with the node, or you can index the full text, or you can index both. It's actually really useful to be able to say, I want to restrict my vector search to rows that also match this specific full text search query. So for instance, vector indexes are not particularly good at very short queries. And so one of the examples that one of our technical field came to me with was she was working with an e-commerce company. And so they wanted users to be able to specify things like red faucet, and if you just use the vector index, it would come back with faucets that were not red, right? So it's like this is also close in the vector embedding space. And so what the way to solve that was to say I'm going to put my red in quotes, and that will tell my application to send that to the full text term matching, and then restrict the vector search to only rows that match that full text predicate.
Interesting. This one hack to exclude the color from the semantic search and perform full text search instead, right?
Right. So under the hood, JVector is wired into Cassandra along with all the other index types that we have. And so you can you can affect the search results by any of the other predicates.
That's cool. So it means that the JVector is just another index for Cassandra, right?
Right. And I mean, there's a little bit more to it than that, in the sense that vector search is approximate by nature, and so that introduces some complexity that you don't need to deal with the other index types. But if you zoom out far enough, then yes, it's just another index.
Okay. So what we have JVector 3, which uses compression and therefore uses significantly less memory than the vector 2. How much less?
As I mentioned, the edge list becomes your bottleneck, and so it's something like 10x less, ballpark.
So what it means is, for usual clients or customers, they would notice that Cassandra is smaller, needs less RAM, right?
That's right. Yes, or alternatively, that you can you can ingest more data in the same amount of RAM. While we were talking, I checked the actual file on disk, and I misremembered. The completed index is 50 gigabytes and not 40 gigabytes.
It's not much, right? Entire Wikipedia.
Yeah. And then there's another. What is 40 gigabytes is the Chronicle Map that stores the article contents. So the total for both of them is about 90.
And you use the Chronicle Map just as a bridge between the cohere model from Hugging Face and JVector?
It's the JVector internal IDs and the text. So when JVector associates integers with vectors, and then when you do a search for another vector, what you get back is a list of integers saying, here's the vectors that I have internally that are closest to what you gave me. And so to turn that into something useful in your application, you need to be able to map those integers to whatever your source form is. And again, when you're using it from Cassandra, Cassandra takes care of doing that mapping for you. But when you're doing it with JVector, raw, then you need to do that yourself. And so that's what Chronicle Map contains: the map of JVector integers to text fragments that correspond to the embedding. Yeah. So it's a map of integer to string in the code.
And so we have the compression. So RAM improvement, the architecture was changed. Is there any other thing you did for 3 or?
Yeah, so we went pretty hard on the compression algorithms that we support. So commonly in the vector search world, you commonly have product quantization, which is what DiskANN introduced, and you have binary quantization, which is a very simple transformation of, for each dimension in your embedding, I'm going to turn that into either a 1 or a 0 bit. So I'm going from 32 bits of a float 32 down to a single bit. And that's popular because you can do it without an external codebook. So with product quantization, you end up with this codebook that tells you what the quantized points correspond to in your original vector space. But for a bunch of database designs, including Lucene, including PostgreSQL, it's really difficult to fit in the concept of, I have this third piece of source of information that was calculated from my original data, but is not the same as my original data. And so binary quantization is super popular with JVector, for instance, because you can quantize it down, you can compress it by a factor of 32, and that's all you need. All you need is that compressed set of ones and zeros. You don't need that extra codebook. The downside of binary quantization is that it is very, very inaccurate, which you would expect. Like, you're just doing this very simple transformation on it. So, for instance, with OpenAI's Ada embedding model, if you index those vectors uncompressed, so with full resolution, and then you search for the top 100 in a data set, then you're going to expect that of those 100 results that you get back from your approximated index, 95% of those, or 95 of those 100 results are going to be in the correct exact top 100. And the way you measure this is you pre-compute offline the correct answers for your data set, and you do that on a large machine with GPUs to accelerate it. And then once you have that answer key, then you can test arbitrary vector indexes to see how good the accuracy is. So if you're doing it with uncompressed, you get about 95% right. If you do it with binary compression, you get about 69% right. So you've gone from 95% to about 70%. That's a pretty meaningful loss of accuracy. If you're using the E5 small v2 embeddings, which is the open source model I mentioned earlier, then you go from about 87% with the uncompressed vectors to 45% with binary compression. So it's really a massive accuracy loss that you get. And so in the DiskANN world, you can say, I'm okay with that because I keep the uncompressed vectors on disk and I can pull them into memory on demand to re-rank the answers that I'm getting from my quantized search. And so in that case, you can trade off less accuracy from your quantization in exchange for faster comparisons. And that lets me go deeper into the graph and then make it up on the re-ranking. It turns out in the case of binary quantization that it's actually a very narrow sweet spot because even with re-ranking for E5v2, for instance, I cannot get that 45% back up to 87% with any meaningful amount of re-ranking. Even if I search 5 times deeper in the graph and re-rank 500 instead of 100, I'm still not getting back up to my original accuracy. OpenAI's Ada v2 and OpenAI's OpenAI v3 small, as well as Coheres. Those are the 3 that I've found where binary quantization can be useful. And even for those 3, I can get even better results using product quantization at 64x. So we did add binary quantization support. It's not as useful in JVector as it is in some of these other options because we have a high quality product quantization implementation as well, and that's usually better. But we do support the binary quantization. Now, something that is less often seen, and in fact, I don't know of anyone else doing it, is refining product quantization with anisotropic weights. And what that is this is an idea that came out of one of Google's vector search papers.
One question regarding the bit level quantization.
Mm-hmm.
Is it worth to trade off RAM for CPU? I mean, because I think CPU is cheaper. So is it always the case that is the way to go, or is it a specific case for specific models?
Other things being equal, I would rather have a smaller footprint in memory. Because that's usually my bottleneck. And the reason is that you need to keep the entire quantized data set in memory to do this coarse search quickly. So if I have 100 million vectors in my data set, I need to keep all of those compressed vectors in memory. And as my data set grows, my memory footprint grows as well. So that tends to become the bottleneck.
Okay, then you're right. So we would like to have to consume less RAM, but we need more CPU. And it's one point of time, I think it's easier to get CPU. I think both is hard, right? If you go to
both is hard, but if you have an application and you have 100,000 users hitting it with requests, that request volume tends to stay similar even as they're generating more and more data that you need to index. And so that's why my default is I'm going to optimize for keeping that memory size low, because that's what keeps growing over time, even if my request volume doesn't.
Yeah, you're right. Because what you are saying is that the CPU requirements are more or less equal, but the RAM will grow because the database gets larger usually, not smaller.
Right.
Yeah, and this is okay. This is actually a good point. What brings me to complete different fact. What happened in projects? We at the beginning of a cloud project, we bought storage which was more cold than warm. So it means at the beginning it was more expensive for us because the API calls were more expensive. But the longer we were in the project, the cheaper it got, because in one point of time it was break even. So we could actually save some money because the size requirements they are getting the size grows over time, so it gets more expensive over time anyway. And this is what you said. This is also smart because you say, okay, because I have to keep the entire database in memory, then it will just grow. This is usual for applications. So, and this is what I cannot control. But seems like the JVector, the CPU requirements are linear, I guess, right? Or is it the
CPU requirements are logarithmic in the size of the data set, assuming that you can keep your index segment count under control.
But still, what I didn't understood completely is if I have multiple Cassandra nodes, the partition key and so forth is so we have consistent hashing. So this was
Yes.
what I consistent hashing. So Cassandra knows where it lives, but the vector is more or less there, and it has to be pre-filled with the data of the specific partition key, right? So what you will need, or no, it doesn't have, right? Because on every insert, okay, this is easier than I thought, because let's say we have three nodes in a cluster. So you go to the leader, you store it to the leader, so leader gets the data. So it is stored into the index like any other index. And then behind the scenes, I don't know whether the gossip protocol is still there. So it gets replicated to the other nodes. And then because it is identical setup, also then is the state of the JVector the same as the other node. So this is non-issue because we're always going through Cassandra, and Cassandra replicates the data because of the consistent hashing, right? So because we know the key, Cassandra knows how to route the data to particular nodes. And this was the idea there.
Right. And you can, Cassandra, you can treat the replication as kind of a black box, because what's going to happen is, even in a simple case like I have 3 nodes, the JVector indexes are probably not going to be identical, because the indexing process is sensitive to the order in which the vectors are inserted and so forth. And Cassandra's replication does not guarantee any specific order that the follower nodes will see those writes in. And in fact, all of the nodes can be receiving writes simultaneously and replicating to the others. And so you will almost certainly, even if you try to stop it, you will almost certainly always see slightly different orders on the indexing. But that's okay. You don't need to care about that at any level outside of, I'm debugging Cassandra's repair code, because Cassandra will take care of that reconciliation at the data level, and then the indexes are all derived from those SS tables that contain the raw data.
Well, it means eventual consistency if the leader stops writing or writes to leader are stopping, then all the followers will get the data anyway, but the data might be in different order. That's what they're saying. And it doesn't matter because the vector is associated with the Cassandra data. So right. So
right.
Yeah. Yes, you're right. I mean Okay, so we have 2 major features: less RAM because of compression, even less RAM because of 1-bit vectorization. So we have almost in minus RAM requirements already.
I want to talk about just one more thing related to the compression, which is the anisotropic product quantization.
Exactly.
So as I was saying, this is something that Google published in one of their vector search papers, and hasn't really it's flying under the radar for most people, I think. And the idea is that if you're doing vector search with cosine similarity, which is the most common way that you want to compare vectors from OpenAI or Cohere or E5 and so forth, if you know that you're comparing with cosine similarity, then you should be able to take advantage of that when you're performing your quantization, so that you care more about angular distance than you do about linear distance. And so the anisotropic PQ is a way to do that. And the other thing you care about is you care more about being relatively accurate for vectors that are close together than you do about vectors that are far apart. If they're far apart, then it's like, okay, they're not going to be in my top 100 search. So I kind of don't care how far apart they are, as long as they sort towards the end of my candidate list. And so combining those two concepts, you can actually make product quantization more accurate. It's just as fast. The similarity computation is the same code, but you're encoding it in a more accurate way. And so you pay a price in terms of extra computation at the encoding time, to get more accurate results at query time. And since almost always you're doing the encoding just once or relatively few times compared to how many searches you're running, so that's usually a good trade.
Mm-hmm.
And then the final, go ahead.
Yeah. So what you said is that there's a different similarity algorithm, and which actually compares vectors close to each other pretty well. And if they are, shouldn't be the default. Where are the cases where the vectors, also the far away vectors, matter? I mean, this would be. Are there any use cases for that?
There aren't really, no. So this is specific to product quantization, where I'm splitting my vectors up into subspaces, and then I'm quantizing each of the subspaces into 256 centroids, and then I encode each of those subspaces as a single byte. And so the anisotropic algorithm is about how do I influence how those 256 centroids are computed so that they give me those two properties of capturing the angular distance and emphasizing the accuracy more heavily for vectors that are closer together.
So almost sounds like consistent hashing.
Okay, yeah, I can see that.
Because of the partitioning, I think. So just, what you also explain, I say, okay, it's partition with bits is like, and this is
right.
why
it's in the sense of where to find it from
exactly.
the property of the key, yes. But actually computing it for product quantization is a lot more difficult, and it's an iterative process rather than performing a deterministic hash on it.
Mm-hmm. And the search is more accurate because I'm searching in subspace, right? And the subspace is smaller, and this is maybe the reason why I get better results.
Right, because I've trained the subspaces, if you will, to encode this angular distance preferentially for vectors that are closer together. And so if I take my query vector and I sum up the dot products with all of the subspaced quantizations, then I've introduced less error in that reconstruction or in that asymmetric computation.
And you mentioned JVector 3 is one of the, or was the only vector database?
I don't know of anyone else doing it, but I could be wrong. There's a lot of vector search projects out there, but I don't know of anyone else doing it. So that's one of the reasons why I feel comfortable telling people that JVector is the most advanced vector index in the world. Not just the most advanced Java vector index, but it's the most advanced vector index.
And you picked Java because you wanted to have a scalable solution. So we had this in the first podcast, right? So
exactly,
which is still amazing because that I'm also amazed of performance of Java, but you have a DB background, which matters even more. The last thing, because then I would like to ask you some questions regarding implementation. So you wanted to mention the last feature of JVector, right? How it's called? Antisomorphic? No.
Anisotropic.
Anisotropic. This is a nice term.
Yes. Yeah, that's... Yeah, I mean,
Could you spell it the first time? Anisotropic?
That's the term that the Google paper uses. I mean, if you just translate it into normal English, it just means weighted. That's all it means. So I guess it sounds more impressive if you call it anisotropic.
Mm-hmm. Should be specific. I cannot pronounce that from CSS. The specificity and anisotropic, and then would be great title for the next paper. Okay, what is the last feature?
We're getting short on time, so I'll just tell you what it is, and then I'll refer our listeners to the JVector README to go into a little more detail. Mm-hmm. But the last one's called Fused ADC, and the way this came about is there's a French SIMD expert, so like the AVX 512 on Intel chips. Neon on ARM chips, the hardware that lets you do multiple operations against a stream of data concurrently on your CPU. And so this is perfect for doing things with vectors, because you have these long streams of float 32s that you want to multiply and add together to compute similarities. And so this Frenchman named Fabien André came up with a way to store the lookup tables for product quantized comparisons in the registers of the SIMD hardware. And so he published 3 papers over the years that refined his solution more and more. The first one was called, it was a long title, but it was the operative keywords are fast scan for doing this accelerated similarity computation. Then the next paper was called Quick ADC, and then the third one was called Quicker ADC. And it's the third one that implements full AVX 512 acceleration against product quantization lookup tables. Super, super interesting. But the long story short is JVector can store those lookup tables in line with the index on disk and pull it out as it's retrieving edge lists, pull it out at the same time with the same disk access, put it into the SIMD registers, and compute the similarities all at once in the same time that we could have done a traditional asymmetric distance computation against traditional product quantization. So I've gone from I need to hold my quantized vectors in memory, and that's my bottleneck. And now I've gone to I don't have any memory footprint. My memory footprint is 2 megabytes. Like that's it. And if you have 100 million vectors, if you have a billion vectors, it's still 2 megabytes. And I'm pulling everything else off from the disk on demand without a speed penalty. So that's the last thing I wanted to mention.
Mm-hmm. But SIMD is CPU still.
SIMD CPU, yes.
Which becomes more and more important, I think, because of the GPU shortage. Is a super interesting, right? That you have a solution which is accelerated on CPU and not necessarily GPU, because they are expensive, power hungry, and not available. So maybe I think in the research, most stuff happens on CPUs, right?
It is true that most of the research has historically been done on CPUs. You are starting to see more research happen about, is there a way that we can accelerate vector search using GPU? The easy way to accelerate vector search using GPU is during index construction. And there's a bunch of people who are doing interesting work in solving that. Microsoft has an open source repository called SPTag that uses GPU to accelerate construction. NVIDIA has one called Cagra that also does the same thing. And then the harder part is, can we also use GPU to accelerate the searches itself? And the reason that's harder is that every time you go to the GPU with a request, there's just this really, really high penalty in terms of launching the kernel. There's a fairly high latency penalty there. And also anything that you need the GPU to compute on, you need to copy into VRAM. And that's also a fairly slow operation. So there's nobody, I would say nobody knows the best way to combine the two. And I think it's fair to say that right now the state of the art is doing searches on CPU.
Mm-hmm. How was the implementation of all the features? What you used, low-level Java, which looks like C, or were you able to use high-level Java constructs, nice code, I don't know, Java records, Java 21 features, and more? So what is the,
Yeah, so the bad news is it's still true that the more you care about performance in Java, the more you end up writing code that looks like C. And so I mentioned that the edge list was our bottleneck. And so originally, the edge list was an array of a class that was nested 3 deep. And so you had a reference to a reference to a reference, and then you would have one of those entries for every edge. And the edge itself was just a 32-bit integer, so it's 4 bytes. So I've got 4 bytes for the edge, and then I've got another 48 or so bytes for my internals. And so that's obviously a really bad efficiency. And so this is I think it's the first time in 20 plus years of writing Java code where I went in and I re-optimized my objects for that memory footprint. And, I'm used to doing it for reducing allocations. I've done that a lot of, everyone knows that, but this is the first time that the reference overhead in that object hierarchy was one of the bottlenecks that we ran into.
Is it a common pattern? What you did that you replaced the object references?
It was specific to the JVector internals.
Okay.
Yeah.
And were you able to use the JVector API, or was it?
Yes. So there's 3 implementations of vector similarity in JVector. One is just normal unoptimized CPU. And so that's because Cassandra still needs to run on JDK 11. And so we have no acceleration at all code path for JDK 11. The second one is for if you have JDK 19 or more recent. This is the last time that they changed the Panama API in an incompatible way for us. So if you have 19 or more recent, then you can use the Panama vector code. And then finally, for the fused ADC, for the part about the transposed codebooks that we put into SIMD registers, that's just way too low level, even for the Panama intrinsics. And so we actually have some C code that we use the Java 22 foreign function API for to leverage. And for that actually is Java 22, because in Java 22, that's where you can have a float array that Java can access and get a pointer to that, a memory segment reference to that, and pass it off to a C API and not have to copy it off into native memory before doing that.
Maybe I asked you this already. Will Valhalla help with specific data types, like float 16 or whatever? Would this help JVector be even faster, or you optimize already that way? I don't know.
So most of the places that people are using float 16, you see Lucene doing float 16, for instance. That's because they don't have product quantization and the re-ranking pipeline. So no, I'm not going to be rushing to add that, because I don't think it solves a problem that we have, since we're all doing much higher compression levels with PQ.
So we covered JVector 3.
Great. Good timing.
I hope, right? So all the features is there. So there's no reason not to use it, right? So just use it as significantly less memory. In best possible case, you will save, so it run on 1/10 of RAM, right?
That's right, yeah. And if you enable the fused ADC, then even less when you're serving the queries.
People...
I'll give one more shout out to that Fuji article about indexing Wikipedia with JVector. That's probably what I'd refer people to if they want to go deeper and say, okay, what does the code actually look like?
Perfect. Where people can find Astra, JVector, Cassandra, and you on the internet?
Well, datastacks.com for Astra, and then I'm on Twitter as Spiced, SPYCED. And then, of course, on github.com/JBEllis, that's where the JVector repository lives, and so forth.
So thank you for your time, and see you next time, maybe in JVector 4, 5, or 6.
All right. Thanks so much, Adam.
Bye.